be an introductory lesson on quadratic functions and equations. More specifically, we will be discussing basic quadratic graphs and their properties. The learning target for this lesson is I can graph quadratic functions of the form y equals ax squared and y equals ax squared plus c. The key idea for this lesson is that a quadratic function is a type of nonlinear function that models certain situations where the rate of change is not constant. If the rate of change of a function is constant, the function will have a graph that is a straight line. If the rate of change is not constant, the graph will be nonlinear, as in the case of the quadratic function. Quadratic functions have graphs that are U-shaped curves, which I will show you in just a moment. Now, the graph of a quadratic function is going to be symmetric, and there will be either a highest point or a lowest point on the graph. If there is a highest point, then that is considered to be a maximum value. If there is a lowest point, then that is going to be a minimum value. So let's consider the basic quadratic function. The most basic quadratic function is y is equal to x squared. Oftentimes we refer to this as the parent function. The graph of this function is a U-shaped curve that has a point at the origin of the graph. So it actually kind of comes down like this and hits the origin. Now, notice that in the case of the graph that I'm drawing, that if it were perfect, which of course the graphs that I draw on the screen will not be perfect, but if it were perfect, it would be symmetric. And by symmetric, I mean that there is an axis of symmetry that passes through the center of the graph. Now, by the center, I'm talking about this point right here, which is known as the vertex of the graph. The vertex of the graph will be either the graph's lowest point and therefore correspond to a minimum value, or it will be the graph's highest point and correspond to a maximum value. Now, the axis of symmetry, which I've drawn here in blue, divides the parabola, which is the U-shaped curve, into two halves that are mirror images of each other. This is what I mean when I say that the graph is symmetric. The axis of symmetry will always be represented by a dashed line. The reason why we dash the line instead of drawing it solid is because this particular axis is not a part of the graph. It is merely a line that represents where the mirror image is occurring. You might look at it as the mirror. So let's work a problem that might help you to understand what these functions are designed to do. Consider the function h of t is equal to negative 16t squared plus c. This function is designed to model dropping an object from a given height. For instance, as a cat walks along the railing of a balcony, it knocks a flower pot off the railing. The function h of t equals negative 16t squared plus c gives the height of the flower pot after t seconds when it falls from a height of c feet. How long will it take the flower pot to reach the ground? Explain your reasoning. Now, what we're going to do is we're going to model the situation as a graph. So the cat is walking along the railing, and it's going to knock the flower pot off, and the flower pot will start to fall. The distance that the flower pot must fall before it reaches the ground is 64. And so 64 represents the original height of the flower pot. Well, according to the problem, C is the height of the flower pot. So I'm going to replace my C value in my equation with 64 and write the equation as h of t is equal to negative 16t squared plus 64. So let's draw a t-table of values and let's plot some points. Now, instead of using x and y in my table, I'm going to use t and h. T for time, h for height. So on my axes of my graph, I will label the horizontal axis t and the vertical axis is going to be labeled h. Also, when we're working modeling problems, we typically label the axes with words. So the time axis will be the horizontal axis, and the vertical axis is height. Okay. Next, what I'm going to do is get some values. Well, in the case of time, we know that at 0 seconds, that the height of the flower pot would be 64 feet. Because, as of yet, at 0 seconds, the cat has not knocked the flower pot off the railing. So the flower pot is 64 feet up in the air. That's how high it is. But once the cat knocks the flower pot off, the flower pot will start to fall. Well, where will the pot be after 1 second? So that would be t equals 1. And to find that value, I would substitute a 1 into my function. And if I put in 1, h of 1 would equal negative 16 times 1 squared plus 64. Well, negative 16 times 1, well, 1 squared is 1, so negative 16 times 1 is negative 16. And negative 16 plus 64 is 48. So after 1 second, the height of the flower pot would be 48. So the flower pot is going to fall 16 feet in 1 second. So let's go ahead and graph that on a graph. So I know my maximum height is 64, so I'm going to put a tick mark here and call that 10 feet and use a scale of 10 on this axis. So 10, 20, 30, 40, 50, 60. So 64 feet would be midway between, or almost midway between, 60 and 70. So I'm going to put it about right there. Okay. Now I know that after 1 second, I will be at 48 feet. So this is going to be 1 second, and now I need to go up to 48 feet. So again, I'm counting 10, 20, 30, 40, 50 is here. You can't really see where I'm putting it, but there's 50. And so 148 would be slightly below 50, so maybe about right there. Try to get that point a little bit on. Okay, so let's see what's going to happen after 2 seconds. So after 2 seconds, where would the flower pot be? So let's plug in 2. And h of 2 is going to be equal to negative 16 times 2 squared plus 64. And since 2 squared is 4, that would be negative 16 times 4 plus 64. And negative 16 times 4 is negative 64 plus 64. Well, that's 0. Well, on my graph, where would a height of 0 be? Well, if you think about it, that would be on the x-axis. So what that means is I'm going to go over 2 and up 0. So that's right there. Let's make that red, like our other points. Okay, so do you see what's happening? And this is what I mean when I say the rate of change is not constant. During the first second, the flower pot only falls 16 feet. But between seconds 1 and 2, or in the second section, it's going to fall 48 feet. See how that rate of change is different? And because the rate of change is not constant, I get a curve. And in this case, it's a U-shaped curve. Now, what you're seeing is only half of the curve. If I could consider negative values, the other half of the curve would be on the other side, and it would be going down like this. And that's what would give me the upside down U shape. And that 64 right there would be considered a maximum value. In this case, that represents the maximum height of the flower pot. The flower pot is 64 feet up in the air. It's never going to be any higher. All it can ever be is lower. And the flower pot in this case will only drop to a height of 0, which is here. These problems, these quadratic functions, can model situations like the one presented here where we have a falling object. Now the question asked us, how long will it take the flower pot to reach the ground? Well, we can see from the graph that it should take the flower pot 2 seconds to reach the ground. So we're going to answer that question in a complete statement. The flower pot will reach the ground in 2 seconds. So I answer the statement with a complete sentence, and that's a good answer to the question that was being asked. Okay, so this is our key concept for this lesson. We're looking at the standard form of a quadratic function. A quadratic function is a function that can be written in the form of y equals ax squared plus c, where a cannot equal 0. We call this the standard form of a quadratic function. Now you might be asking yourself the question, well, why can't a equal 0? So let's just write out what would happen if a equals 0. So I'll write it up here at the top. If I have the quadratic function y equals ax squared plus bx plus c, and I let a equal 0, well, what would happen is that would put a 0 value in for a, then I would have plus bx plus c, and then that particular term of the quadratic function would go away because 0 times anything is 0. So then I would just be left with bx plus c. And that particular function is linear, not quadratic. So that is why we have to put in this particular phrase where a does not equal 0 in order for this to be the standard form of a quadratic function. Now, when you're working with these functions, we have what is called a parent function, and it's y equals x squared. The reason we call this a parent function is because it's the simplest quadratic function, and it basically gives us the shape and certain properties for all quadratic functions. So let's graph very quickly the parent function y equals x squared. So I'm going to draw a t-table. I'll draw it over here on this side. And it's going to be an xy table. I'm going to be working with an x-axis and a y-axis. And I just want to graph some points. So to illustrate the basic parabola, I'm going to graph the following points: -2, -1, 0, 1, and 2. Now these values are called domain values. Recall from previous lessons that domains are your input values. And in the case of these basic functions, they correspond to your x values. Now, when we actually put our domain values into our function, what we will be computing are the range values. These are going to be our output values. And in this case, those correspond to the y values. Now keep in mind, not all of our functions will have x and y as the two variables. So x and y is more generic. It can change. In the case of the problem we worked on the previous slide, our domain values were our t values, and our range values were our h values, or our heights. Now, if I put in -2 into that function, I'm going to be placing it in there as y equals -2 in parentheses squared. And since a negative times a negative is a positive, that's a +4. The same will happen with negative 1. When I place negative 1 in for x, then the negative 1 goes in parentheses, and negative 1 squared is negative 1 times negative 1, which is positive 1. 0 squared is 0. 1 squared is 1, and 2 squared is 4. So notice that we have some range values that are repeating. The 4 is repeating, and 1 is repeating. But notice how 0 does not repeat. 0 in this case for this function is the only range value that does not repeat. And that's going to be important to the shape of this graph. So let's go ahead and graph these points. My domain values are negative 2, negative 1, 0, 1, and 2. My range values go up to 4. 1, 2, 3, 4. So that gives me the basic points that I'm going to plot. So negative 2, 4 would be about right here. Negative 1, 1 here. 0, 0. 1, a positive 1, and then 2, 4. Notice how I get some symmetric points. And you're going to see the symmetry just a little bit better once I actually draw the curve. So let's draw the curve. It's going to be a U-shaped curve. We call it a parabola. And it looks like that. Okay. Where is the y-intercept for this particular curve? Well, notice that it occurs at the minimum point of the parabola, right here. So in this case, the y-intercept, 0, 0, is also what we would call the vertex of the curve. It is also at 0, 0. The vertex is either the maximum or minimum point along the parabola, or the highest or lowest point on the parabola. And it corresponds to either a maximum or minimum value. In this case, since the vertex is a minimum, or it's at the lowest point, it corresponds to a minimum. The minimum value is 0. We'll be talking more about maximums and minimums as we go through this course. Now, where is the axis of symmetry? We discussed this on a previous slide. Well, remember that the axis of symmetry is going to come down through and it's going to act like a mirror for the parabola. It's going to basically split the parabola into two halves that are mirror images of each other. When we express the axis of symmetry, we express it as a line. It's a vertical line. And all vertical lines are written in the form of x equals, and then it's whatever x equals, or whatever the x value is for all of the points along the line. In this case, since the vertex point is 0, 0, right here, and the x value of that point is 0, that means that this line is the line x equals 0. So we write the axis of symmetry as x equals 0. Again, x equals 0 represents a vertical line, and the vertical line is the axis of symmetry. The axis of symmetry will always pass through the vertex. So you can always look to the vertex to give you your axis of symmetry. So let's discuss the last thing on my list here, which is end behavior. End behavior is what's happening on the ends of the graph. Now, when you get into more advanced courses, you're going to talk about the way that you're actually going to write the end behavior. For right now, I just want you to look at where my arrows are on my curve. See how they're always pointing up? That means that the end behavior of the graph is increasing on both the positive and for both positive and negative x values. So I want you to just write for me, for right now, that it's increasing. Later on in this course, we'll talk more about better ways that you can actually state the end behavior. But I just want you to notice for right now that this graph does increase for both positive and negative values in the domain. Okay, so let's talk about what's going to happen when our a value is a negative. Now keep in mind that the a value is the value of the quadratic term. That is this it's the coefficient on the quadratic term. So if you look at the first term of the quadratic function in standard form, the a value will be the coefficient of the x squared term. So in this case, my a value is equal to a -1. And I'm asking you the question, what happens when a is a negative? So let's graph negative x squared. Again, I'm going to plot some values. Now, these values, I'm still going to use the same numbers, -2, -1, 0, 1, 2. But then I want to plug in to y equals negative x squared. So this is how you plug that in. You put the negative sign, and then you put the negative number in parentheses, and you square it. Now remember, according to order of operations, you always raise your exponents, and before you actually multiply. So in this case, you're going to leave that negative alone, and you're going to raise -2 to the second power. Well, -2 to the second power is a +4. And because there was a negative out front right here, that means that the answer will be negative. So basically what the negative out front here is going to do is it's going to make all of the values for y, all of your range values, it's going to make them all negatives. So if I put in a -2, I would get -4. If I put in -1, I get -1. 0 should be 0, 1 should be 1, -1, and 2 should be -4. So again, the negative preceding the x squared term is just going to take the graph of y equals x squared, and it's going to negate all of the range values. So my domain in this case is my x values. When you're asking yourself questions about the domain, you want to say, well, what numbers could I put in for the domain? And the answer to that is I could put in any real number. So my domain, the way that I'm going to write this is all real numbers, because I can use any real number in the domain. But once we graph this, I want you to think about what your range values will be, because you can kind of look at the table and figure out that they're all going to be negative. But let's look at the graph. So again, I'm going to label my graph numbers. So -1, -2, +1, +2. So this is a scale of 1. And then now we're going to go negative. Okay, so -2, -4 would be here. -1, -1 would be here. 0, 0, 1, 1, and 2, -4. Notice how it took the graph of y equals x squared and it flipped it over. So now my parabola, my U-shaped curve, looks like this. And all of my values in my range, whereas they were positive for y equals x squared, they're actually going to be negative for y equals -x squared. So my range is y values are going to be less than or equal to 0. And if you think about it, the end behavior helps you to understand this as well. Because what's happening here on the ends of my graph? Is my graph increasing or is my graph decreasing? Well, my graph is decreasing. It's always getting smaller. So I have a maximum value for this graph sitting right here. The maximum value is 0. And that's also what tells me that my range values are always going to be less than or equal to 0. And this right here should be maximum, not minimum. A lot of times we just shorten that to max. And the max value is 0. It's the highest point on the curve. Where is my vertex? Well, again, it's 0, 0. And the axis of symmetry, again, is falling down straight through here, like so. And it also is at 0, 0. Oop, I almost wrote that wrong. Let's erase that. Okay, try again. So my axis of symmetry is going to be x equals 0. Do you see where the y-intercept would be? Remember that the y-intercept is always where x is equal to 0, so it is the point 0, 0. So let's look at another situation. Now let's graph y equals 3x squared. In this situation, I'm trying to look at what happens when I change the value of my a. So now the a value is going to equal a 3. And I want to discuss with you the domain, the range, the y-intercepts, all of this same information for this particular graph when y equals 3x squared and the a value has a value of 3. So again, let's graph this. To graph it, I'm going to use those same points that I've been using. For these graphs for today's assignment, you can use these points. So I'm going to use -2, -1, 0, 1, and 2. And think about this question, what values of x could I use? Well, I could use any real number. I'm just choosing to use those values. So my domain is, again, all real numbers. But my range is going to be the one that's going to change. So we can look at the range once we graph it. So let's go ahead and put in some values in here. And I'll just start with 1, and the rest of these you can do in your calculator. The first one will be y equals 3 times -2 squared. So I'm just putting in this value right here, this -2 in, and I'm going to get my output value, my y value. So remember to do your exponents first. -2 squared is 4, and then 4 times 3 is 12. If I put in a -1, then -1 squared is 1, and 3 times 1 is 3. If I put in 0, 0 squared is 0, and 3 times 0 is 0. That's going to be, by the way, my same vertex. When I put in a 1, my 1 also is going to output a 3. And 2, because 2 squared is 4 and 4 times 3 is 12, is going to output a 12. So again, I'm getting this situation of where I have range values that are repeating. See, the 12 repeats and the 3 repeats. 0 does not repeat. In this case, 0 will be my vertex point. By the way, the vertex is not always at 0. Okay, so let's graph these points. So again, I've got -1, -2, 1, and 2. And because those are the values that I'm using for my domain, or the domain values that I've chosen. And then we're going all the way up to 12 this time. So in order to fit 12 on my graph, I'm going to change my scale. I'm going to use a scale of 3 here and a scale of 1 here. When I need to label my axes, I'm not sure I did that on the last graph, so please remember to label your axes. 3, 6, 9, 12. So this is where 12 is going to be up here at the top. Okay, so -2, 12 is a point. -1, 3. Oops, so that'll be right here. I started to put it in the wrong place. 0, 0. That's going to be my vertex, which in this case will be a minimum. 1, 3 here. And 2, 12, which is all the way up here. So I can now draw my parabola like so. Okay. So what happened with this particular graph? Well, it would be a little easier to see if I had not used a scale. So what I'm going to do here is I'm going to draw just another little picture for you and show you what would happen if I used a scale of 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then 1, 2, 1, 2. See how if I used a scale of 12 and I started to graph this, you can kind of see what it's doing a little bit better. And then there's 1, 3, and then there's 2, 12. Like that. What does that 3 do to the graph? Well, what it actually does is it makes it much skinnier than the graph of my parent function, which was y equals x squared. So when you change the value of a in the function, that value of a is going to determine how skinny or how fat that graph is, because it's going to determine how quickly the graph is going to rise. Okay. So in this case, the range of my function is pretty easy to see. My minimum value is 0. My vertex then is 0, 0. And my axis of symmetry is, let's see, we don't need a parenthesis there for this one. My axis of symmetry would be x equals 0. Just as in my previous function. So let's draw in the axis of symmetry so you can see it a little bit better. So there it is. It's x equals 0. And my range value, though, if you look at it, my range value is all my y values. See how they're always going to be positive? So in this case, the range value is y is greater than or equal to 0. Because my y values are always going to be positive. That is, they're always going to be greater than 0. And they can also be equal to 0 because remember I have that minimum point of 0, 0 on the graph. This graph is increasing. And it has a y-intercept of 0, 0. Now, in this case, the y-intercept and the vertex are indeed the same point. Okay, let's look at another situation. Now we're going to graph y equals x squared minus 4. So the question that I'm asking is, what happens when I change the value of c? So again, let's plot some points to get a picture of what the graph is going to look like. So I'm going to again use -2, -1, 0, 1, and 2. And when I put in a -2, y is going to equal -2 squared minus 4. And -2 squared is 4, so that's 4 minus 4, which is 0. So -2, 0 is a point. What about -1? If I do -1 squared minus 4, that's going to give me 1 minus 4, which is -3. If I put in 0, that's going to give me 0 minus 4, which is -4. If I put in 1, again that's 1 minus 4, which is -3. And 2, well 2 squared is 4, and 4 minus 4 is 0. So again, I'm still getting some y values that are the same, these and these. And then here, notice that this does not have a repeated y value, a repeated range value. That is going to be the vertex of my graph. Notice that it's no longer 0, 0. Now this is 0, -4. So let's graph these points. Again, I'm going to use a scale of 1 along my x-axis. Oop, that's a positive 1. And 2. This is the x-axis. This is the y-axis. -2, 0 would graph, let's change colors here. -2, 0. -1, -3 would be here. 0, 4, or 0, -4 would be down here. And then 1, 3 would be here. Notice how I'm getting these points. These are reflection points, by the way. They're mirror points. Okay. And I can draw my curve, and it's going to look something like this. So do you see what happens when I change the c value here to -4? Do you notice what happened to the graph? Well, the graph translated 4 units down. Translating just means it moved. So it vertically shifted or vertically moved 4 units down from the original position of y equals x squared. So I'm going to go ahead and plot y equals x squared in red. Y equals x squared is right there. And I need to kind of draw it a little lower because it needs to hit the vertex here. So y equals x squared is this graph in red. And by taking and putting a -4 there, it shifted the graph down 4 units. So anytime I change that value of c, that's what's going to happen to these graphs. So what is the domain of the graph? And again, I'm looking at this green graph. My domain of this graph is all real numbers. For all quadratics, we're looking at all real numbers as the domain. That just means that I can put any number in for x that I want to. But my range is my output values. And since my minimum point is -4, that's my minimum, and my vertex is sitting at 0, -4, and my axis of symmetry is x equals 0, So let's go ahead and draw that in. So here's the axis of symmetry. So what that means for my range is that my range values are always going to be greater than or equal to -4. Now, looking at the green graph again, not the red, but the green, where is my y-intercept? Well, my y-intercept over here is this point, 0, -4, because the y-intercept always occurs where x is equal to 0. What about the end behavior for this graph? Well, this graph is a graph that's always, it's increasing on both ends. Okay, so it just increases. In other words, as my domain values, my x's get greater, it's increasing. As my domain values get smaller and smaller and smaller, all of my negatives, my graph is also increasing. We'll talk more about this end behavior later, but I just want you to start kind of getting it into your head what end behavior is. Okay? Okay, so let's look at an application of this. This is very similar to the original problem that we worked in the Getting Ready section of the lesson. An acorn drops from a tree branch 20 feet above the ground. The function h equals -16t squared plus 20 gives the height h of the acorn in feet after t seconds. What is the graph of this quadratic function? And at about what time does the acorn hit the ground? Well, the first thing to tell you about these functions is that these functions are modeling positive situations. In other words, we're not going to have a negative time. So when you look at how I've drawn the graph for this, I've only drawn the positive quadrant of the graph. And the x-axis, or the horizontal axis, represents time. And the vertical axis represents height. And both height and time will be positive. So I'm going to label this t, and I'm going to label this h. So let's get a graph for this situation. Again, I will be able to pick t values. Now, in this case, my domain, my t values are always going to be positive. So I'm going to choose 0 seconds, 1 second, 2 seconds. And then I'm going to figure out my corresponding values of h. So if I put in a 1, I would get put in 0 rather, I would have -16 times 0 squared plus 20. Well, since 0 squared is 0 and -16 times 0 is 0, then the height at 0 seconds would be 20. That's the maximum height of the acorn, which makes sense because the acorn is dropping from a tree branch 20 feet above the ground. So I'm going to use a scale of 5 on my graph and go 5, 10, 15, 20. And I'm going to graph my original height as a height of 20 on my graph. Now let's put in a 1. If I put 1 into my function, I would have -16 times 1 squared, which is -16, plus 20, that would be 4. So after 1 second, the height of my acorn will be 4 feet. So it's just above the ground, probably sitting about right here. So again, let's put him in green at about 4 feet. So the acorn after 1 second is almost to the ground. Let's see what would happen after 2 seconds. Well, after 2 seconds, I'm going to have -16 times 2 squared plus 20. Well, 2 squared is 4, and -16 times 4 is -64. And -64 plus 20 is going to be -44. So at 2 seconds, not only has the acorn hit the ground, but at 2 seconds, it's actually gone negative, which can't happen. So what that tells me is that the acorn is going to hit the ground somewhere between 1 second and 2 seconds, and probably closer to 1 second than to 2 seconds. So I can get an estimate from the graph, and I'm going to estimate that it's going to take about 1.1 seconds for that acorn to hit the ground. So this would be the graph of my quadratic function. But the second question they asked me is, about what time does the acorn hit the ground? So the acorn is going to hit the ground when the height is 0. So again, I want you to really think about what I just said. The acorn will hit the ground at a height of 0. Ground level is 0 numerically. So to solve for the actual number of seconds that it's going to take the acorn to hit the ground, I'm going to replace h in my function with 0, and I'm going to solve. Now, this particular function here is what we're going to be learning to solve in this chapter. Okay, so let's solve this. I'm going to subtract 20 from both sides, and that would give me negative 20 equals negative 16t squared. Then I'm going to divide both sides by negative 16. And I'm going to come up here and write this because I'm running out of room. So that would give me, so negative 20 divided by negative 16 is 1.25. So 1.25 is equal to t squared. Then to solve this, I take the square root of both sides. And the square root of 1.25 is approximately 1.1. So notice that I got the same result by solving this as I did when I estimated it off the graph. So this acorn is going to hit the ground at about 1.1 seconds. Okay, so to wrap this up, we have been talking about a quadratic function. A quadratic function is a type of nonlinear function that models certain situations where the rate of change is not constant. Remember that if the rate of change were constant, our graph would be linear. To illustrate this, I will graph for you y equals 2x. Do you remember that one? Remember, if I chose values such as negative 1, 0, and 1, I could graph this. And negative 1 would output negative 2, 0 would output 0, 1 would output 2. And so my graph would look something like this. Negative 1, negative 2, 0, 0, 1, 2. And it's a graph that is a straight line. The reason it's a straight line is because the rate of change is constant. Rate of change is the difference in your y's over the difference in your x's. And in this case, the rate of change is 2. The rate of change actually corresponds to this number here. It's the slope of the linear function. Quadratic functions are different though. The rate of change is not constant. So to illustrate this one, I'm going to do y equals x squared. For y equals x squared, when I start graphing those points, and the points we normally graph, at least for right now, are negative 2, negative 1, 0, 1, and 2. And we plug those values in, and I would get 4, 1, 0, 1, 4. We've already graphed this one. Now, my rate of change is not constant, and this is going to produce a situation where I have a curve. So this is x, and this is y. I should have labeled these as well. And so negative 2, 4, negative 1, 1, 0, 0, 1, 1, 1, 2. I get this U-shaped curve, like so. Remember, that's because the rate of change is not constant. Therefore, this is not linear. Remember that the graph of a quadratic function is a symmetric curve. They will have an axis of symmetry that passes through the vertex. In this case, the axis of symmetry is x equals 0. And the vertex point is that lowest point. It is the point 0, 0, right here. We see it in the table. Now, in this case, too, the vertex is a low point along the graph, and that corresponds to a minimum value. So that's what this right here is saying to you. We're going to have a symmetric curve with the highest or lowest point corresponding to a maximum or minimum value.